Hello guys, welcome back to Maison African Motives, still on engineering science that is working on the heat. We are going to be focusing on the question paper of April 2023, that is question 8.1. So we just have to see what you're given here. I think it was 13 marks, that is 13 marks in this case, everything. So let us see what we are given. The first part of our question we are given, that is 8.1 in this case. All right, 8.1, let me just try to increase this side. All right, so 8.1, you're given that a man buys 10 liters of paraffin at a shop with a room temperature of 21 degrees Celsius. So this is the initial temperature, which is the room temperature. He places the can in a boot. So take note, he's putting in the boot of his car. So in this boot, what is happening definitely is moving there. The temperature is going to increase. So while driving back to his house, the temperature in the boot rises to 38 degrees Celsius. If the coefficient of volume expansion of paraffin in this case is 796 times 10 to the exponent of minus 6 per Kelvin, calculate the increase in volume at 38 degrees Celsius, which means we're talking about the change in the volume, the increase in the volume, the change in the volume. There is an increase because of the temperature increase from 21 to 38. Given our volume expansion per Kelvin in this case does not even affect our calculation. If you add 273 here, if you add 273 here to Kelvin, you're going to subtract, meaning to say you're going to subtract again 273 minus 273. So that one does not even affect us in our calculation that we are given per Kelvin, and our temperature is given in degrees Celsius. One and the same thing. All right, so that is what you're going to have in this case. What is important, let us take our information so that we can attempt our question in this case given. Like I said, this is 8.1. So we've got the volume in liters in this case. So this is our volume of 10 liters from a temperature of 21 degrees Celsius, which is our initial temperature of 21 degrees Celsius, to a temperature of 38 after the increase. So this is at 38 degrees Celsius, and also given the volume expansion. Remember, our volume expansion is given as gamma in this case. All right, so this gamma is for volume expansion. All right, so we've got the coefficient of linear expansion, which is alpha. Then we have got for area expansion, which is beta. Then we've got for volume, this one is what? It's gamma. So this one from beta, we know that beta is simply equal to 2 alpha. Then gamma is simply equal to 3 alpha in this case, which is the linear coefficient of what? Of expansion. But this one, we are given direct the volume of expansion, not the linear. So we are given direct this one as 764 times 10 to the exponent of minus 6 per Kelvin in this case. All right. So from our information, the question is for us to calculate the increase in volume, which is the change in volume. So the change in volume, if we were given in terms of linear expansion, it was going to be 3 times alpha. But we are not giving the linear. We have direct our volume expansion. So we are not going to use this one. We are going to use the volume expansion as it is times the original volume in this case times the change in temperature. So we have got the change in temperature. Like I said, it does not affect in this case of per Kelvin, because if you add 273, you are going to subtract it again. So it cancels. So used as they are. So in this case here, we are going to substitute our values. Take note, this volume is in liters. So meaning to say the change in volume is going to be in liters again, unless you want to change to cubic meters, but you can just use as it is, all right? So that is 764 times 10 to the exponent of minus 6 times the original volume, which is in liters in this case. So we've got 10 liters times the change in temperature. Simply means we talk about T2 minus T1 final minus initial. So this is going to be our T2, that is 38 degrees Celsius minus 21 degrees Celsius in this case. All right, so this is going to give us the change in volume. An increase, that's a positive. A decrease or a decrease in volume is a negative. So this one, if you are to calculate properly, we are going to obtain 0.12988 liters. Like I said, this is in liters, 10 liters. So that is to 3 decimal place. This one is going to affect to a 10. So you're going to have 0.130 liters or 0.13 liters. All right. So this is our change in volume. It's a positive, meaning to say that's an increase. If it was a negative, it means we are talking about a decrease in that case. All right. Then we've got 8.2. On 8.2, we are given that here the volume of a certain gas is at a temperature 32 degrees Celsius, and we are given a pressure of 0.15 megapascals. In this case, is 39 cubic meters. All right. So if the temperature now stays at 32, take note of the information. The temperature stays at 32 degrees Celsius, meaning to say we are talking about a constant pressure. This is the effect of what? The effect of gases. So they are talking about constant temperature. Sorry, this is temperature, the one that is not changing. All right. If pressure is not changing, that is a constant pressure. But here it is the temperature which is maintaining 32 like this. All right. So that is an isothermal process. So this one is given a special name. Remember this special name. This is isothermal process. So that's an isothermal process where we've got a constant pressure. So a constant temperature in this case. And the pressure decreases to 5 kilopascals. Calculate the volume of the gas. All right, so you need to calculate the volume in this case. All right, so let us take our information aside. This is question 8.2. So let us just try to have our values aside. So if you are to take note, we have got the initial conditions of the gas in this case, which is the initial conditions are at 32 degrees Celsius at this pressure, and we are given the volume in this case. All right, so take note, we have got T1, P1, and we are taking as they are. So we have got our temperature, T1, 32 degrees Celsius. So T1 is at 32 degrees Celsius. Remember, our pressure was 0.15 megapascals in this case, which is same as 0.15 times 10 to the exponent of 6 in pascals. In this case, just direct pascals, all right? Then we also have the initial volume of the gas. So the initial volume is the one that you are given as 39 cubic meters. The volume is 39 there. So you're given the volume of 39 cubic meters. So we're going to have our volume of 39 cubic meters. All right, list your information properly. Then we are told that it is at a constant temperature, meaning to say our T1 is going to be maintained at 32 degrees Celsius. There is no change in temperature there. It's constant. That is isothermal process. But the pressure changed. In this case, it dropped or it decreases to 5 kilopascals. That is a change. Then calculate the volume. So meaning we need the volume after this change in the pressure that happened, having our P2 as 5 kilopascals. So given that it decreases to 5 kilopascals, what is going to be the corresponding volume there? That is our question. So from our laws of gases, we understand that the pressure, so in this case, pressure times volume, we can say P1 V1 over T1 is equivalent to P2 V2 over T2 when we are given pressure and volume at the same time and having our temperatures at the same time. All right. So noting that T1 and T2 are the same. Yes, we can use this as it is on our formula, but here these two are the same, T1 and T2. So meaning to say, instead of having this, we can simply cancel these two because they are the same. So we can write our formula as instead P1 V1 is equivalent to P2 V2 since temperature is the same. Our question is to calculate V2, so we can make V2 the subject of the formula, in this case by dividing by P2, both sides, the pressure here. So that means we can say at the end, our V2 can be written as, that's P1 times V1 over P2. And we have all these values. We've got P1 in this case. This is our P1, the first pressure that you're given, which is at 0.15 times 10 to the exponent of 6 times V1. We have V1, which is 39 in this case, everything over P2. Our P2 in this case, which is 5 kilopascals, that's 5 times 10 to the exponent of 3. So we're going to have 5 times 10 to the exponent of 3 in this case. So like I said, guys, you could have worked this with T1 and T2. You're going to see that you have the same answer. So instead of doing that, just remove that because these two are the same, so you can simply cancel them. All right. So now we can say that from our calculator, we can conclude that the second volume is going to be 1170. So you're going to have 1170 in this case. All right. Which is in cubic meters, the same part that we had before. This was in cubic meters. So meaning to say, we are also going to have our value in cubic meters. All right. So that was the first part of our question on 8 point, that is the second part, sorry, 8.2. So this is the second part. Let us check what we have on 8.3. 8.3 we are given, so this is our 8.3 here. So we have got the volume of, okay, let me put it this way. We are given the volume of a helium gas. So this is a helium gas that you're given at 10 degrees Celsius. Let us try to list our information. That's question 8.3. So we have got the initial values in this case, right? We are still on the application of gases again, just like the previous part. So here we are given that the volume of helium gas is at 10 degrees Celsius. The pressure in this case being at 700 kilopascals is, so the volume there is the one that you're given. So you're given the volume there corresponding as 0.42. So we've got 0.42 cubic meters. At this pressure, so this is our initial pressure of 750 kilopascals in this case. The initial temperature corresponding there being 10 degrees Celsius. All right, so we're going to have our temperature at 10 degrees Celsius. All right, so take note. Having, if we are to work with this volume, it's in cubic meters, our pressure in kilopascals in this case, and and we check here. I want us to check something. If we check something here, sorry for this one. I want you to see something again. I wanted to check on this part. I don't want to have a confusion here. If we are to check on our previous question when I was referring to this part here, because of the formulas that we actually used or the application of these formulas that we had, and having our constant temperatures, and we neglected our temperatures here, this does not mean that we are not supposed to work with our temperature in kelvins in this case. We could have worked with our temperature in Kelvin. We are going to add 32 plus 273. You obtain your temperature in Kelvin. The same thing here. But since we were not considering this temperature on our calculation, like I said here, from these formulas that we are going to have, we canceled and we ended up using the formula where the temperature is not involved. That's why I never talked about the Kelvin part here. It's because we are going to cancel these temperatures. But on this one, if you are to take note of the information that we have, we are not even having the condition of a constant temperature. So meaning to say our temperature now has to be converted to Kelvin. We are supposed to work with this temperature because we are to use this temperature this time. On our last part here, we are not using, but if we are to use that one, even if you're to like both 32 and 32 cancel, so the effect there is not considered. But on this one, be careful how you're given your question. So here, make sure, so it is best that you just convert in each and every question that you're given so that you do not confuse where you do not know where to convert or where not to convert. All right, so like I said, we are going to have in kelvins our temperature. So it's 10 degrees Celsius. So meaning to say in kelvins, our temperature is going to, you add 273 to convert to kelvins, you add 273. So this is going to give us 283 in in kelvins in this case. All right. So this is our initial information. The gas constant is at 2,08 kilojoules per kg Kelvin. All right. We are given the coefficient, that is the gas constant in this case, that is R in this case, being 2,08 kilojoules per kg Kelvin. All right. Then our question is to calculate the mass of the gas, which is 3 marks. All right. With this information that we have, I want you to see, guys, we cannot relate the part of P1, V1, that part that we had, because we do not have conditions of the second part of the gas, what happened later on. We are just given initial values. All right. It follows that in this case, if we are to consider that we do not have these conditions, the product of the pressure, I want you to see this, the product of the pressure to the volume, in this case, we can say that P, okay, let me use it from this one. We can say that PV in this case, which is the product of the pressure to the volume, is equivalent to MRT. If you are working on the second conditions, we are going to work with P2, V2, T2. What can change in this case? These are pressure, volume, temperature. In this case, we are referring to the initial conditions. So this is our P1, this is our V1, this is our T1. So like I said, these values, they can change depending with what you are given. So from this one, we can see that, okay, we need to calculate the mass. So we can make our mass the subject in this case, all right? So we can divide by RT1, in this case, divide by RT1 both sides. So this can cancel so that we remain with the mass. So the mass is going to be P1 V1 over MT1. We have these values, so meaning to say we're going to substitute our P1. And I also want to take you into consideration to say that if we are given our pressure in kilopascals here, it does not affect our gas constant in kilojoules per kg Kelvin. Instead of changing these kilopascals to normal pascals, we can use this as it is both. This is in kilo, this is in kilo again. So that means we are going to have our P in kilopascals as it is, meaning to say that is going to be 750 times V1, our V1, which is 0.42. Everything over M, which is, in this case, why am I having M now instead of R? Okay, so this is R. Sorry for that, guys. Remember, this is R. So we're going to have our R in this case, which is 2.08. Like I said, kilopascals, kilojoules. So we're just going to leave it like that, all right? Times T1, which is our initial temperature in kelvins, because this is per Kelvin, okay? Per kg Kelvin. So that is 280 and 83. So with this information, even if we were to use times 10 to the exponent of 3 times 10 to the exponent, still it's fine, but it's not even necessary in this case. All right, so having this on our calculator, we are going to obtain the value of the mass. So our mass in this case is going to be 0.535 to 3 decimal places. Remember, our mass being measured in kilograms, that is in kgs. All right, so that is how we can play around with our formula. So this formula, we can calculate P1, we can calculate V1, we can calculate mass, we can calculate temperature, we can calculate even the gas constant. Depending with what you're given, you can make anything the subject of the formula. That's what I'm trying to say. All right, so let us check the other part of our question in this case, which is 8.4. On 8.4, we are given that a rectangular prism of aluminum has dimensions. So these are the dimensions of a rectangular prism. Remember, a rectangular prism, we are talking about a solid figure in this case, or a solid shape. So on a solid shape, we talk of volume. In this case, we refer volume. If we are talking about just a normal plane shape, we talk of area from there. So here, It's a solid shape. So these are dimensions which gives us the volume of the rectangular prism. Remember that the volume of a rectangular prism is given as length times width times breadth in this case, or length times width times height. Some they use length times width times the breadth in this case. All right. So here we have got the volume. At a temperature of, which is the initial temperature in this case, our T1, it is heated to 45 degrees Celsius, which means we are talking about the second temperature. The increase is an increase from 18 up to 45. Calculate the volume at 45 degrees Celsius. Not the increase in volume, but the volume at what is going to be the volume there. So we're talking about the final volume that is going to be affected, whereby our final volume, we understand this is going to be the change in volume plus the original volume that we are given. The original volume, like I said, from the dimensions that we are given here, we are going to obtain the original volume in this case. All right. So this is what you're going to have on our information. So this is question 8.4. Like I said, we are given, this is an aluminum prism. So from the aluminum part, if we are to check in our information sheet, you are to check there on the aluminum, the linear coefficient of expansion of aluminum. If you check on your information sheet, you are going to have this as your linear coefficient of expansion is going to be 23. So check properly on your information sheet. Is 23 times 10 to the exponent of -6 degrees Celsius. All right. So that is what we have from the aluminum part. So these dimensions, they give us the volume. So we are going to have the volume as you multiply 45 times 36 times 28. These are in millimeters. So if you multiply, you are going to obtain 45,360 cubic millimeters, which you can convert to cubic meters if you want. But since we are to calculate the volume, you can use that volume in cubic meters. So there's no need also for us to convert that to cubic meters. We can just use the cubic centimeters, cubic millimeters, whatever that you're given. Sometimes they can even give you liters. You can use also liters as they are instead of what? Converting. All right. So our question is that we are supposed to calculate the final volume because this is the volume at, not the change. Take note of this question here. This one which asked us here, do we have this one? Is it on this one? Calculate the increase, this one on the first part, the increase in volume. Take note about this one. This is the increase at, the increase at. Then we need the volume. What is going to be the volume at? The volume, that is the final, just like this question here, which is calculate the area of copper at. This is the final area there, not the change in area. What is going to be the final area, meaning to say we are supposed to add. So in this case, we need the final volume, not the change in volume. But in order for you to have the final volume, you need the change in volume in that case. All right. So our change in volume, we have this formula before. We said our change in volume is going to be given as the last part we were given the volume expansion, which was gamma. But this time we do not have, we are given alpha, we are given the linear coefficient of expansion on our information sheet. So meaning to say our gamma in this case, which is the volume expansion, this one is our volume expansion, is going to be 3 alpha. Remember, I talked about this before. So meaning to say, we can now use our formula instead of gamma, because it was supposed to be like this, was supposed to be gamma times the original volume times the change in temperature. In this case, we're supposed to have the change in temperature in this case. But if we are to consider what we have here, we can substitute, instead of having this gamma here, we can substitute with this one, with the 3 alpha. So that means this one can be written as the change in volume is given as 3 alpha in this case for the volume expansion, times the original volume. In this case, we're going to multiply to the original volume times the change in temperature in this case. All right. So we have all these in our information, I didn't talk about the temperature. Why? We've got our temperatures here. Remember, it was at 18. Our initial temperature is at 18 here. This was our initial temperature, our T1 at 18 degrees Celsius. And the final volume at 45, the temperature there, it's at 45 degrees Celsius. All right, so that is these are our temperatures. So we are going to substitute these into our formula so that we can calculate our change in volume. So therefore, our change in volume is going to be 3 times the linear coefficient of expansion. So this is your linear coefficient of expansion of 23 times 10 to the exponent of -6 times the original volume in this case, which is, you can write those dimensions, multiply them, or you can just write this final answer that we got, which is 45,360 in cubic millimeters. Take note, these are cubic millimeters, all right? Times the change in temperature, which simply means T2 minus T1. So this is our change in temperature, T2, which is 45 degrees Celsius minus T1, which is also 18 degrees Celsius. So this is going to give us the change in volume of 84. So you're going to obtain 84,506. So this is 84,506. This was in cubic millimeters. So your answer is going to be in cubic millimeters. If you were using cubic, if you were using here cubic meters, if you convert it to cubic meters, meaning to say your answer is going to be something like 85,506, something like that, 506, like this. All right, it is going to be 506 times 10 to the exponent of -9 cubic meters. So instead of just use the cubic millimeters, is fine like that. All right. So our question was to calculate not the change in volume, the one that we are having here, not the change in volume, but the final volume, the volume at. This is your final volume. So our final volume, therefore, can be given as, remember, we say the final volume is equivalent to the change in volume plus the original volume. So our change in volume, depending with what you are using, if you are using cubic millimeters, we are going to have this as 84, that is 84, not 85. This is 84 in this case, where 84 here. So this is going to be 84,506, all right, which is in cubic millimeters. So we also add the original volume in cubic millimeters. This one, our original volume. This is our original volume of 45,360. So we are going to obtain our final volume in this case of 45,444. So you're going to have 444,506 cubic millimeters. If you were using the cubic meters, it is going to be something like 45,444,506 times 10 to the exponent of -9 in cubic meters, if you are using that, okay, which is fine, but you can just use it as what? In cubic millimeters, because we are not told leave your answer in these units. All right, so take note also when you're revising with your memo, sometimes you might find them not writing the final answers, ending up at a certain point. No, you do the correct thing on your exams. All right, so that was our question 8.4. Then 8.5, we have got a similar question just to this one. This time we are given that we have got a copper plate. So this is a copper plate with the dimensions of 105 millimeters by 645 millimeters, just like the same question. So these dimensions are for area. We are given two values, this one by this one. So this is for area. So we are talking about length times width or length times breadth. So this is for area. If you are given 3 values, that is for volume. 2 values for area. So we are given the area part in this case that you're having here, which is our original area in this case. All right, so this is 8.5. All right, so like I said, we have got the original area in this case, which is given as 105 by 642, which is going to give us something like 67410. That is 410 in this case. square millimeters, which you can convert to square meters if you want. One and the same thing. We can work this in square meters or in square millimeters. It's one and the same thing. So we are given that this is a copper plate, all right? So a copper plate, if you are to check on your information sheet, the copper plate has got the linear coefficient of expansion of 17 times 10 to the exponent of -6 per degrees Celsius. So this is given per degrees Celsius, all right? It is being heated, okay, at a temperature of 15 degrees. This is our initial, the one that it was at. So after it was then heated now from the 15 degrees Celsius, we are seeing that it was later heated to a temperature of, which is our second temperature now, of 325 degrees Celsius, our final temperature. Calculate the area of the copper plate at. What is this type of equation? Calculate the area at. That is our final area there. Not the increase, not a decrease, but the final area. So just like what we calculated from the previous case, our final area, therefore, definitely is going to be given as our final area is going to be the change in area that we are going to calculate plus the original area, whereby we need now to calculate the change in area or the increase in area, depending to say, is there an increase or not? From the previous part, I talked about the relationship that occurs or that takes place between the linear coefficient of expansion to the area coefficient, because whenever you're going to calculate the change in area, you're going to have our formula as the area expansion, because we talk about area. So it is going to be the beta in this case for the area of expansion times the original area times the change in temperature. But because here we are given the linear coefficient of expansion, we are going to say, remember I said from this, our area expansion is going to be given as 2 alpha. The volume expansion is given as 3 alpha. So take note, you need to understand this. Where alpha is your linear coefficient of expansion, the one that you're given on your information sheet. So that means we can be able to calculate this one by substituting now the area expansion in place of what? In place of our area expansion, we can substitute this as 2 alpha. So that means our change in area is going to be given as 2 alpha. So we're going to have 2 alpha in this case times the original area. So we're going to have the original area times the change in temperature, which simply means T2 minus T1, just like what we said before. So let us substitute our values and see what we are going to have. The change in area is going to be given as 2 times the linear coefficient of expansion of 17 times 10 to the exponent of -6 times our original area, working with the square millimeters as they are, meaning to say our answer is going to be also in square millimeters. So this is, we are going to multiply 67410 times the change in temperature, which simply means T2 minus T1, just like the previous part. So it's 325 minus 15 degrees Celsius, our initial. So we're going to subtract 15. So we are going to obtain an increase there because that's a positive value that you're obtaining. So in this case, we are going to obtain our change in area as 700. So this is going to be 710,5014, something like that, in square meters. All right. Or we can just use 501 after 3 decimal places, which is fine. But our question is not to calculate the increase in area, but it is to calculate the area at that point, which is the final area in this case. And we said our final area can be calculated from this formula, the change in area. So we are going to check now our increase in area, which is our change in area, the one that we got here. That is 710, 5014 plus the original area, since we used square millimeters, add also the original area in square millimeters. If you use square meters, then also use square meters, all right? So we are going to add 67410. So this is 410. So if we add, we are going to obtain our final value, which is going to be 68120, 5104, which is at 3 decimal place. You can just leave it like this in square millimeters. All right, so take note of your information that you're given. So this is how you can answer these typical questions. What you need is to take note of the units that you're given, work with the units properly, apply your units properly on your formula. That is how you can have these typical questions. But for now, that's it from Maison African Motives. Till we meet again.